A microscopic grain of common table salt resting on the tip of a stainless steel knife appears to be the ultimate expression of domestic stability and safety. In this crystalline form, the substance is so benign that it is added to almost every meal consumed by the human species, serving as an essential nutrient that regulates fluid balance and nerve impulses. However, this granular piece is the result of a profound chemical ceasefire between two of the most aggressive and unforgiving elements in the periodic table. If the microscopic treaty holding this crystal together were to be dissolved, the result would be the release of two lethal materials: a soft metal that explodes upon contact with H2O and a suffocating pale green gas that aggressively dismantles biological tissue. This gas is chlorine, the 17th element, and its biography is a study in extreme duality. It exists as a green despot, an element defined by an atomic scale hunger so intense that it functions as one of the most powerful oxidizing agents in existence. To understand the modern world is to understand how human ingenuity learned to cage this volatile gas within the rigid geometry of a salt shaker, turning a chemical weapon into the primary guarantor of urban hygiene and industrial manufacturing. Subscribing to the channel and contributing a perspective in the comments ensures that these detailed investigations into the substances that build our world continue to reach those who seek a sophisticated understanding of the elements. The physical reality of chlorine, Cl2, in its elemental state is a radical departure from the white, odorless crystals found on a kitchen table. When isolated, chlorine manifests as a heavy, yellowish-green gas with a distinctive, suffocating odor that can be detected at concentrations as low as 3 parts per million. This gas possesses a density approximately 2.5 times greater than that of standard air, which dictates its behavior in a gravitational field. If released into an environment, chlorine does not dissipate upward like steam. Instead, it behaves like a visible, fluid-like fog, pooling in low-lying areas, trenches, and basement floors. This heavy characteristic is a direct result of its atomic mass, where 2 chlorine atoms bond together to form a diatomic molecule. In this state, the element is a relentless hunter of electrons, a characteristic driven by the fundamental architecture of its electron shells. To explain the reactivity of chlorine on the fingers, one must examine its valence shell. A chlorine atom possesses 17 protons in its nucleus and 17 electrons orbiting it. These electrons are arranged in layers, and for chlorine, the outermost layer contains exactly 7 electrons. In the rigorous world of atomic physics, there is a principle known as the octet rule, which dictates that an atom achieves maximum stability when its outer shell is occupied by 8 electrons. This makes chlorine an atomic seeker, with a single, high-stakes missing piece. It is like a high-speed machine that is perfectly functional except for one missing gear. To find that missing electron, chlorine will strike almost any other material it encounters, ripping electrons away from metals, organic molecules, and H2O. This process is known as oxidation, and in chlorine, it occurs with such ferocity that it can be described as a slow-motion fire that does not require a spark to ignite. The salt crystal, or sodium chloride, NaCl, represents the total satisfaction of this atomic hunger. To understand why table salt is so stable, one must look at its partner, sodium. Sodium is a group 1 alkali metal that possesses a single electron in its outermost shell, an electron that it wants to get rid of just as much as chlorine wants to acquire one. When these two elements meet, they do not merely mix, they undergo a total energetic transformation. The sodium atom physically transfers its lone outer electron to the chlorine atom. This exchange transforms both into ions. The sodium becomes positively charged, and the chlorine becomes negatively charged. Because opposite charges attract with immense force, they lock together into a cubic lattice, a molecular prison, where the green gas and the explosive metal are neutralized. This ionic bond is so powerful that it requires temperatures exceeding 1,474 degrees Fahrenheit just to melt the crystal. In this state, the chlorine is no longer a despot. It is a passive participant in a rigid structural grid, rendered harmless by the very theft of an electron that defines its nature. However, when this despot is liberated from its salt prison through the process of electrolysis, its aggressive engineering characteristics return immediately. In an industrial setting, high-voltage electricity is passed through a brine solution, forcing the sodium and chlorine to relinquish their ionic bond. As the green gas bubbles to the surface, it immediately seeks to revert to a state of lower energy by reacting with anything in its path. If a piece of iron wool is placed in a jar of pure chlorine, the reaction is spontaneous and spectacular. The iron atoms are stripped of their electrons so rapidly that the metal begins to glow and emit clouds of brownish-red iron chloride. This is not combustion in the traditional sense of burning in oxygen, but a purely chlorinated fire. The chlorine acts as the oxidant, demonstrating that oxygen is not the only element capable of sustaining a destructive energy release. The biological impact of chlorine is equally uncompromising, rooted in its interaction with H2O. When chlorine gas comes into contact with the moist tissues of the human body, such as the eyes, the throat, and the delicate alveoli of the lungs, it does not simply sit on the surface. It reacts with the H2O present in the mucus and cellular fluid to produce a mixture of hydrochloric acid, HCl, and hypochlorous acid, HOCl. These acids act like microscopic chemical saws, dismantling the proteins and lipid bilayers that form the walls of living cells. To explain this on the fingers, the chlorine gas effectively turns the body's own moisture against itself. The resulting damage is a form of chemical pneumonia, where the lungs become inflamed and fluid-filled as the cellular structures dissolve. This lethal efficiency is the reason why chlorine was the first element to be weaponized on a massive scale, shifting the history of warfare from the mechanical to the molecular. Yet, this same destructive potential is what makes chlorine the most effective sanitarian in human history. The ability of hypochlorous acid to rip through the protective envelopes of viruses and the cell walls of bacteria is what allows for the sterilization of the global H2O supply. In a modern water treatment facility, a microscopic dose of chlorine, often less than 1 part per million, is injected into the flow. On an atomic scale, this creates a kill zone for pathogens. The chlorine ions hunt down the enzymes responsible for bacterial respiration, short-circuiting the organism's ability to process energy. This is a purely mechanical victory of chemistry over biology. The reason why the 21st century citizen does not fear the water-borne plagues that devastated the 19th century, such as cholera or typhoid, is entirely due to the presence of this __15__ patrolling the pipes of the city. The engineering of chlorine also extends into the realm of material science, specifically in the creation of the polymers that define the modern landscape. Polyvinyl chloride, or PVC, is a material where chlorine atoms are woven into a long chain of carbon and hydrogen. In this configuration, the chlorine does not act as a gas or an acid, but as a structural stabilizer. Because chlorine atoms are large and carry a significant negative charge, they provide a __16__ effect that makes the plastic resistant to fire and chemical degradation. Without the presence of these chlorine atoms, the plastic would be far more brittle and prone to breaking down under ultraviolet light. The very __17__ nature of the element, its refusal to let go of its bonds, is what provides the longevity for our window frames, our credit cards, and our underground plumbing. To look at a salt shaker today is to witness a managed chemical apocalypse. We are utilizing an element that is fundamentally incompatible with life to protect the very foundations of our civilization. Chlorine is a material that demands an absolute respect for its thermodynamic boundaries. It is either our most lethal enemy or our most vital protector, with no middle ground. The quote 18 of salt is that we have found a way to take the most, quote 19, element in the cosmos and satisfy its hunger so completely that we can safely place it on our tongues. It remains the silent architect of our safety, a shimmering green ghost of the stars that has been tamed by the geometry of the crystal, reminding us that in the universe of the small, the difference between a poison and a cure is often nothing more than the arrangement of a single electron. The existence of chlorine across the cosmos is a testament to the high-stakes nuclear ledger of the universe, representing a material that is forged not during the stable youth of a star, but during its desperate and terminal struggle against gravitational collapse. While elements such as carbon or oxygen are produced in massive quantities during the long, rhythmic middle age of a celestial body, chlorine occupies a more precarious position in the atomic hierarchy. It is a product of __quote_20__. Specifically, the oxygen-burning and neon-burning phases that occur only in the most massive stars, those possessing at least 8 times the mass of our own Sun. To understand the origin of the green gas currently locked within a common salt crystal, it is necessary to look back billions of years to the interior of a dying giant, where the temperature has reached a staggering 1.5 billion degrees Fahrenheit. In this extreme thermal environment, the star has exhausted its primary fuels of hydrogen and helium. To prevent its own mass from crushing the core into a singularity, the star begins to quote _21_quote its own ash. This process is a sequence of increasingly frantic nuclear reactions, where the nuclei of lighter elements are forced together with such violence that they overcome their natural electromagnetic repulsion. Chlorine is synthesized through a pathway known as the alpha process, where a nucleus captures a proton or a helium nucleus. Specifically, the isotope chlorine-35 is often the result of oxygen atoms smashing into one another. However, there is a fundamental law of nuclear physics known as Harkin's rule, which dictates that elements with an even atomic number are significantly more stable and abundant than those with an odd atomic number. Because chlorine possesses 17 protons, it is inherently more difficult for the universe to manufacture and maintain than its neighbors, sulfur, 16, and argon, 18. It is a scarcity element, a material produced in the narrow margins of a cosmic catastrophe. The distribution of this newly forged chlorine into the interstellar medium is a consequence of the star's final act, a core collapse supernova. When the nuclear furnace can no longer provide the outward pressure to resist gravity, the core implodes, triggering a shockwave that ejects the star's outer layers into the void at a significant fraction of the speed of light. The chlorine found on Earth today is essentially the __quote_23__ from these ancient explosions. For millions of years, this chlorine-rich dust drifted through space as part of a massive, cold cloud of molecular gas. When this cloud eventually collapsed under its own gravity to form our solar system approximately 4.6 billion years ago, the chlorine was incorporated into the rotating disk of matter that would eventually become the planets. The arrival of chlorine on the infant Earth was governed by its extreme chemical reactivity and its classification as a __quote_24__ element. In the early solar nebula, chlorine often existed as hydrogen chloride, HCl, a gas that would have easily been swept away by the intense radiation and solar wind of the young sun. If the Earth had relied solely on its atmospheric gases, the chlorine would have been lost to the vacuum of space, leaving the planet as a chemically stunted wasteland. The reason the Earth retained its chlorine supply is due to the elements underscore underscore quote underscore 25 underscore underscore atomic nature. Chlorine is a chalcophile and lithophile element, meaning it has a strong affinity for bonding with metals and being incorporated into silicate rocks. During the molten stage of the planet's formation, the chlorine atoms did not remain in the air. They immediately sought out partners in the cooling crust. The most significant of these partners was sodium. This was the most important chemical marriage in the history of the planet. Sodium, an alkali metal, possesses a single loosely bound electron in its outermost shell that it is desperate to shed. Chlorine, as previously noted, has 7 electrons and is desperate to acquire an 8th. When these two elements encountered one another in the roiling magma and the early oceans, they formed an ionic bond of near unbreakable strength. This reaction transformed a volatile gas and a reactive metal into sodium chloride, NaCl, or common salt. By bonding with sodium, the chlorine was anchored to the planet. It became too heavy to escape the atmosphere and too stable to be destroyed by radiation. As the Earth cooled and the first rains fell, a second planetary scale process began: the creation of the world's oceans. Over hundreds of millions of years, H2O flowed over the volcanic rocks of the continents, leaching out the soluble minerals. Because sodium chloride is highly soluble in H2O, the oceans became the ultimate terrestrial reservoir for chlorine. Today, chlorine is the most abundant dissolved ion in the sea, accounting for approximately 1.9% of the total mass of seawater. If the world's oceans were to be evaporated entirely, the resulting salts would form a layer of mineral over 150 feet thick across the entire surface of the planet. The sea is, in a very real sense, a liquid archive of ancient stellar processes, a massive brine-filled vault that has held the universe's, quote, 28 in a state of ionic suspension for billions of years. The geological history of chlorine is also marked by the formation of, quote, 29, massive underground deposits of salt that serve as the primary source for modern industrial extraction. These deposits are the result of ancient, landlocked seas that were cut off from the global ocean and subjected to the relentless heat of the sun. As the H2O evaporated over millions of years, the concentration of salt reached a tipping point, causing the sodium chloride to precipitate out of the liquid and settle into thick, crystalline layers. In places like the Permian Basin in the United States or the Zechstein Sea in Europe, these salt beds can be thousands of feet thick and buried under miles of sediment. These are the underscore underscore quote underscore 30 underscore underscore of the chemical world, waiting for human industry to pump in fresh H2O, dissolve the salt back into brine, and bring the chlorine back to the surface. This cosmic and geological journey defines the current underscore underscore quote underscore 31 underscore underscore of the element. We do not find chlorine in the air we breathe or in the rocks we use for construction. We find it almost exclusively in the salty depths. The fact that any of it is available to us at all is the result of a series of specific coincidences. The precise temperature of an oxygen-burning star, the explosive release of a supernova, and the chemical underscore underscore quote underscore 32 underscore underscore that allow the fugitive gas to be caught and held by a metal. We are utilizing a material that spent eons as a drifting vapor before it was, quote, 33, quote, by the Earth's gravity and oceans. When we look at the ocean or a salt mine, we are looking at the final resting place of a stellar traveler. The chlorine ions in every drop of salt water have remained unchanged since they were first dissolved in the primordial H2O billions of years ago. They have witnessed the arrival of life, the shifting of continents, and the rise of humanity. The quote 34 did not disappear. It simply waited in the shadows of the salt lattice, its aggressive potential held in check by the laws of thermodynamics. To extract chlorine today is to perform a reverse engineering of the planet's early history, using electricity to break the bond that sodium and chlorine formed in the fires of the infant Earth. We are reaching into a 3-billion-year-old liquid archive to liberate an element that was born in the heart of a dying giant, proving that even the most abundant substances on our planet are the survivors of a long and violent cosmic lottery. The chlorine in our world is a permanent reminder that the stability of our environment is built upon the captured remnants of a celestial chaos that occurred long before the sun ever shone. The historical trajectory of chlorine is a narrative defined by a profound cognitive dissonance, where a single substance transitioned from a misidentified laboratory byproduct to a catalyst for the global textile industry, before ultimately precipitating the most traumatic shift in the history of modern warfare. This journey began in 1774, within the modest laboratory of the Swedish pharmacist Carl Wilhelm Scheele. To understand the conditions of this discovery, one must look at the prevailing scientific paradigm of the 18th century, which was dominated by the quote, 35 theory. At that time, chemists believed that all combustible materials contained an invisible, weightless quote 36, called phlogiston, which was released during burning. This theory acted as a conceptual prison, blinding researchers to the true nature of the gases they were isolating. When Scheele reacted the mineral pyrolusite, manganese dioxide, MnO2, with a solution then known as spiritus salis, or hydrochloric acid, HCl, he produced a choking, yellowish-green vapor that exhibited a startling ability to extinguish the color of flowers and leaves. The engineering of this observation was a masterclass in pre-modern chemical analysis. Scheele noticed that the gas was not merely a variant of standard air. It possessed a density that caused it to settle in the bottom of his glass vessels and a solubility in H2O that produced a highly acidic liquid. However, because he was a prisoner of the phlogiston theory, he did not recognize he had discovered the new element. He named the substance, quote, 37, believing that the gas was hydrochloric acid that had been stripped of its, quote, 38 by the oxygen in the manganese. It was an instance of a researcher holding the key to a fundamental atomic truth while lacking the theoretical framework to turn the lock. It would take another 36 years and the rigorous intervention of the English chemist Humphry Davy in 1810 to prove that this green gas was an elementary substance. Davy gave it the name chlorine, derived from the Greek quote, 39 signifying its pale green hue, and in doing so, he dismantled the last remnants of the phlogiston era, revealing chlorine as a primary agent of oxidation. Before its darker applications were realized, the industrial drama of chlorine centered on its extraordinary ability to manipulate the aesthetics of the human world. Prior to the 19th century, the process of bleaching textiles, turning raw, grayish linen and cotton into brilliant white fabric, was a logistical ordeal of extreme geological and temporal requirements. Fabrics had to be soaked in sour milk or lye and then spread across vast quote 40 to be exposed to the sun for months at a time. This was a process of solar oxidation, where the ultraviolet radiation from the sun slowly broke down the organic pigments in the fibers. It was an inefficient use of land and time that could not keep pace with the accelerating output of the Industrial Revolution. Chlorine provided the chemical quote 41 .
The transition from solar bleaching to chemical bleaching represented the first large-scale industrialization of chlorine. By capturing the gas in a solution of lime to create calcium hypochlorite, or bleaching powder, manufacturers could achieve in hours what previously took an entire season. To explain this on the fingers,
chlorine acts as a quote, _42 ___. The pigments that give color to a fiber are complex organic molecules with long chains of alternating double bonds. Chlorine atoms, with their intense hunger for electrons, strike these molecules and break those double bonds, effectively shattering the quote, _43 _ structure of the pigment. The light no longer finds a surface to bounce off in a specific frequency, and the fabric appears white to the human eye. This engineering breakthrough allowed the textile industry to move indoors, decoupling the production of clothing from the cycles of the seasons and the availability of sunlight. Chlorine became the quote, _44 _ a substance that brought a standardized industrial whiteness to the masses. However, the 19th century success of chlorine as a domestic servant masked a latent capacity for mass destruction that was fully unmasked in the early 20th century. This shift from the quote 45 of the textile industry to the quote 46 of the battlefield is inextricably linked to the work of Fritz Haber, a German chemist who remains the most controversial figure in the history of the elements. Haber, who had already revolutionized the world by creating synthetic nitrogen fertilizers, recognized that the massive surplus of chlorine produced by the German chemical industry could be repurposed as a tactical tool to break the stalemate of trench warfare. In the spring of 1915, near the Belgian town of Ypres, also known as Ypres, the first large-scale deployment of a chemical element as a weapon of war took place. The engineering of the Ypres gas attack was a feat of atmospheric logistics. Because chlorine is 2.5 times heavier than air, it does not rise and dissipate into the upper atmosphere. Instead, it obeys the laws of fluid dynamics, flowing across the terrain like a heavy, invisible syrup. Haber and his team installed 5,730 pressurized cylinders of liquid chlorine along a 4-mile stretch of the front line. When the valves were opened on April 22nd, the liquid chlorine vaporized into a dense, yellowish-green cloud that was carried by a gentle breeze toward the Allied trenches. To the soldiers on the ground, this was a phenomenon for which no defensive protocol existed. The cloud did not pass over the trenches. It sank into them, filling the low-lying fortifications and dugouts with a suffocating concentration of the 17th element. The causal chain of the physiological destruction caused by chlorine at Ypres is a masterclass in the lethal intersection of chemistry and biology. As the soldiers inhaled the gas, the chlorine atoms encountered the H2O-rich environment of the respiratory tract. The resulting chemical reaction produced a mixture of hydrochloric acid, HCl, and hypochlorous acid, HOCl, directly on the delicate membranes of the lungs. To explain the engineering of this failure on the fingers, these acids acted like microscopic saws, dissolving the lipid membranes of the alveoli, the tiny sacs where oxygen and carbon dioxide are exchanged. This triggered a massive inflammatory response, causing the lungs to leak cellular fluid into the air spaces. The victims were not poisoned in the traditional sense. They suffered from quote 47 effectively drowning in their own internal fluids while standing on dry land. Within minutes, a 4-mile gap was torn in the Allied line, and the nature of global conflict was permanently altered. The historical drama of this event lies in the sudden realization that the same substance used to sterilize the bedsheets of hospitals and the clothing of cities could be used to erase the lives of thousands of individuals in a single afternoon. The Ypres attack triggered a rapid evolutionary race in material science, the development of the gas mask. The first primitive respirators were essentially pads of cloth soaked in sodium hyposulfite, or even human urine, utilizing the chemical's ability to neutralize chlorine through a redox reaction. This was the first time in history that the survival of an army was dictated by its ability to maintain a portable chemical laboratory on the face of every soldier. The green cloud of chlorine became a permanent shadow over the 20th century, leading to the signing of the Geneva Protocol in 1925, which sought to ban the use of such asphyxiating, poisonous, or other gases in war. Despite this legal and moral condemnation, the despot could not be discarded. The Haber-Bosch process, which relied on chlorine-based chemistry for various secondary steps, continued to feed the world, and the demand for chlorinated plastics began to climb. The element had developed a dual identity. It was the angel of sanitation and the demon of the trenches. This duality was further complicated in the mid-20th century by the discovery of the environmental persistence of chlorinated organic compounds, such as DDT and PCBs. These molecules, which utilize the stability of the carbon-chlorine bond to create long-lasting pesticides and insulators, were found to accumulate in the food chain, leading to the collapse of bird populations and the contamination of the world's oceans. It was a secondary historical drama, where the very stability that made chlorine useful in engineering became a liability for the biosphere. To look at chlorine through the lens of history is to see a material that has been used to edit reality. We used it to edit the color out of our fabrics, to edit the pathogens out of our H2O, and eventually to edit human beings out of the landscape. It is a substance that demands a high level of technical mastery and an even higher level of ethical restraint. The stain on the soul of chlorine is the memory of Ypres, a green scar that serves as a reminder that the most essential tools of civilization are often the ones that are the most difficult to tame. We have moved from Scheele's confusion to Haber's calculation, and finally to a state of modern dependency, where we rely on the 17th element for our safety, while remaining acutely aware of its potential for chaos. Chlorine is the element that taught us that chemistry is not a neutral science, but a high-stakes dialogue between our desire for order and the inherent volatility of the atomic world. It remains the most powerful sanitarian in our inventory, a shimmering green ghost that has been successfully redirected from the battlefield back to the water treatment plant, proving that the destiny of an element is ultimately determined by the intent of the hands that release it. The invisible architecture of the contemporary city functions as a massive, synchronized apparatus designed to maintain a state of biological and industrial sterile peace, a feat made possible only through the relentless chemical work of the 17th element. While the public consciousness often associates high technology with the glow of silicon chips or the efficiency of lithium-ion batteries, these innovations rest upon a foundation established by the green despot. Today, chlorine operates as the primary sanitarian of the human species, performing a role so fundamental that its removal would result in the immediate regression of urban centers into the plague-ridden landscapes of the 19th century. This transition from a weapon of the trenches to the guardian of the faucet is a masterclass in the redemption of a material through engineering. The most pervasive and critical application of this element is the disinfection of the global H2O supply, a process that represents the single most significant public health advancement in the history of civilization. To understand the engineering of water chlorination, one must examine the microscopic battlefield that exists within a common municipal pipe. Before the standard application of chlorine, drinking H2O was a primary vector for pathogens such as Vibrio cholerae and Salmonella typhi. These microorganisms are essentially biological machines designed to exploit the fluid environment of the human body. Chlorine neutralizes these threats through a process of systemic molecular dismantling. When chlorine gas, Cl2, or sodium hypochlorite is introduced into H2O, it reacts to form hypochlorous acid, HOCl. This molecule is the silent assassin of the microscopic world. Unlike many other disinfectants, hypochlorous acid carries no electrical charge, which allows it to function as a molecular lockpicker. The cell walls of bacteria are typically negatively charged, creating an electrostatic shield that repels many chemical intruders. Because hypochlorous acid is neutral, it slips past this electric fence unnoticed. Once inside the bacterium, the chlorine atoms initiate a catastrophic causal chain. They target the proteins and enzymes responsible for the organism's metabolism, specifically those that facilitate the movement of nutrients and the production of energy. The chlorine rips electrons away from these vital structures, causing the proteins to unfold and lose their functional shape, a process known as denaturation. This is the biological equivalent of a saboteur entering a power plant and physically melting the copper wiring and gearboxes. The organism does not merely stop functioning, it physically disintegrates at the molecular level. This process occurs with such efficiency that a concentration of less than 1 part per million is sufficient to ensure that the H2O flowing into a high-rise apartment is safer than the pristine mountain springs of the pre-industrial era. We live in a world where the threat of H2O-borne pandemics has been effectively edited out by the constant presence of the 17th element. The influence of chlorine extends beyond the biological and into the structural, serving as the essential hardening agent for the polymers that define the modern physical environment. Polyvinyl chloride, or PVC, is the third most widely produced synthetic plastic polymer in the world, and it is a material that would be physically impossible without the heavy, stabilizing presence of chlorine atoms. If one examines a standard credit card, a section of underground sewage pipe, or the frame of a high-efficiency window, they are looking at a carbon-based skeleton that has been armored with chlorine. In the manufacturing process, chlorine is bonded to ethylene to create vinyl chloride monomer, which is then polymerized into long chains. The presence of the chlorine atom in this chain is a masterpiece of atomic scale fortification. Chlorine is a large electronegative atom, and when it is woven into the polymer structure, it provides two critical engineering advantages: durability and fire resistance. To explain this on the fingers, a simple plastic like polyethylene is like a thin, flexible string of paper clips that is easily melted or torn. By adding the bulky chlorine atoms, engineers turn that string into a reinforced cable. The chlorine atoms act as molecular anchors, increasing the attractive forces between the polymer chains and making the material rigid and resistant to the crust rot of environmental degradation. Furthermore, chlorine is a natural flame retardant. If a PVC pipe is exposed to heat, the chlorine atoms release a gas that smothers the flame at the surface, preventing the plastic from becoming a fuel source. This is the reason why the hidden infrastructure of our buildings, the wires and the H2O lines, is encased in a chlorinated shield. It is a material designed to endure for a century while remaining indifferent to the threat of fire. Perhaps the most sophisticated and least recognized role of chlorine is its function as the chemical scalpel in the global pharmaceutical industry. It is a staggering reality of modern medicine that approximately 85% of all pharmaceutical products are manufactured using chlorine chemistry at some stage of their synthesis, and nearly 25% of all final drug molecules contain chlorine atoms as a functional part of their structure. In the laboratory, chlorine is the ultimate placeholder and reactive handle. Because chlorine is so eager to react, chemists use it to grip onto a molecule, pulling it into a specific shape or forcing it to bond with another substance. It acts like a temporary set of surgical clamps that allow the builder to assemble a complex molecular structure before the clamps are removed. However, in many life-saving medications, the chlorine atom stays in the final structure to perform a specific biological task. In many antibiotics, such as vancomycin, or in medications that regulate blood pressure, the chlorine atom acts as a molecular wedge. Because of its size and its specific electrical pull, the presence of a single chlorine atom can change the way a drug molecule twists in three-dimensional space. To explain this on the fingers, a drug molecule must fit into a cellular receptor like a key fits into a lock. If the key is slightly too loose, it won't work. By inserting a chlorine atom at a precise location, the chemist can, quote, _75 _quote, the key, ensuring it fits perfectly into the target and triggers the desired healing response. Without the 17th element acting as this __quote, _76 __, the vast majority of our modern pharmacopoeia would be biologically inert, incapable of docking with the complex proteins that govern our health. The high-tech economy also relies on chlorine for the purification of the materials that drive the digital revolution. The production of hyperpure silicon, the substance used to manufacture the microchips in every smartphone and computer, is a process governed by the __quote, _77 __. Raw silicon is extracted from quartz, but it is filled with impurities that would render a processor non-functional. To clean it, the silicon is reacted with hydrogen chloride, HCl, to form trichlorosilane, a liquid that can be distilled with surgical precision. This distillation removes every stray atom of iron, aluminium, or boron, leaving behind a quote _78 quote that is then reduced back to its elemental form. This is a process of quote _79 quote, where chlorine is used to carry the silicon through a cleansing furnace before being discarded. Similarly, the production of titanium for aerospace applications relies on the Kroll process, which uses chlorine to turn titanium ore into a gas so it can be purified. Chlorine is the __quote _80 _ of the high-tech world, the element that vacuums the impurities out of our most advanced materials to ensure they operate at the limits of physics. Even the convenience of the modern diet is a byproduct of chlorine's ability to manipulate the sensation of sweetness. Sucralose, a common zero-calorie sweetener, is produced by taking a molecule of sucrose, common sugar, and replacing 3 specific oxygen-hydrogen groups with 3 chlorine atoms. This __quote _81 _ is a feat of precision engineering that changes the molecule's fate in the human body. The presence of the chlorine atoms makes the molecule unrecognizable to the enzymes that normally break down sugar for energy. To the human tongue, the __quote _82 _ still fits the __quote _83 _ perfectly, providing the sensation of sugar. But to the digestive system, the molecule is a foreign object that passes through without being metabolized into calories. This is the __quote _84 _ turned into a sensory illusionist, using its atomic weight to bypass the laws of human metabolism. The __quote _85 _ of chlorine is therefore a narrative of total integration. We do not see the green gas, but we live within the whiteness of its bleached paper, the sterile safety of its H2O, the rigid durability of its plastics, and the targeted healing of its medicines. It is a material that provides the structural and chemical __quote _86 _ necessary for a high-density civilization to function. Chlorine is the element of __quote _87 _ the substance that cleans our silicon, fortifies our infrastructure, and tunes our biology. Every time a credit card is swiped or a glass of H2O is consumed, the 17th element is performing its duty as the silent architect of the modern condition, proving that even the most volatile and quote, 88 elements can be harnessed to provide the highest level of safety and convenience, provided they are managed with absolute engineering rigor. Without this quote, 89 patrolling our pipes and laboratories, the complex, high-speed reality of the 21st century would succumb to the chaos of infection and the fragility of unfortified materials. The permanence of chlorine on a planetary scale is not a function of its presence in the atmosphere, but rather its absolute dominance within the global hydrologic system. While the previous historical and industrial narratives of the 17th element focus on its transition into a volatile gas or a structural plastic, the enduring legacy of chlorine is written in the liquid salt of the world's oceans. Every atom of chlorine that currently facilitates the digestion of food in a human stomach or serves as the structural backbone of a polyvinyl chloride pipe is merely a temporary visitor from a massive 3-billion-year-old reservoir of salt. This element does not follow the rapid, recycled paths of carbon or nitrogen, which move between the air and the soil in a matter of years. Chlorine follows a trajectory of extreme geological patience, moving through a cycle where a single quote 90 can take hundreds of millions of years. This unique characteristic ensures that chlorine is the ultimate stabilizer of the planet's chemistry, acting as a primary buffer that prevents the Earth's oceans from becoming either too acidic or too basic to support the evolution of complexity. The most intimate record of this planetary history is carried within the biological fluids of every living human. To understand the quote 91 that chlorine provides, one must analyze the composition of a human tear or a drop of blood. These fluids are essentially refined samples of the primordial ocean, maintained at a specific salinity to ensure the functionality of cellular life. Within the human stomach, chlorine performs its most critical metabolic role as a component of hydrochloric acid, HCl. This is the quote 92 of the body. To explain the engineering of this process on the fingers, the stomach lining possesses specialized cells called parietal cells, which function as microscopic chemical pumps. These pumps pull chlorine ions out of the bloodstream and combine them with hydrogen to produce an acid so powerful it can dissolve a piece of zinc or steel. The purpose of this quote 93 is not merely to break down food, but to perform a precise structural dismantling of proteins. The high acidity forces the complex, folded chains of proteins to unravel, exposing their individual links to the body's enzymes. This is a high-stakes chemical operation where the body utilizes the quote 94 element to destroy foreign matter while protecting itself through a thick, regenerative shield of mucus. Without the constant availability of chlorine ions to maintain this internal furnace, the energy acquisition of the human species would stall, and the biological machine would fail. In this sense, we are saline-filled vessels, walking extensions of the ancient sea that have learned to carry the 17th element within us to power our thoughts and movements. Beyond the biological realm, the legacy of the 20th and 21st centuries will be permanently recorded in the Earth's crust through the presence of chlorinated technofossils. The most significant of these is polyvinyl chloride, or PVC. In the natural world, the bond between carbon and chlorine is relatively rare and difficult to produce. However, human industry has manufactured hundreds of millions of tons of this polymer, embedding it into the infrastructure of every continent. Because the carbon-chlorine bond is one of the strongest and most stable in organic chemistry, PVC possesses a degree of environmental resistance that borders on the geological. To explain this on the fingers, most bacteria and fungi have evolved biochemical teeth to bite into the carbon-hydrogen bonds found in wood, leaves, or even some simple plastics.
But the bulky electronegative chlorine atoms in PVC act like a layer of molecular armor. The decomposers of the biosphere simply do not have the tools to break this bond. Consequently, when the cities of the modern era eventually collapse and are buried under layers of sediment, the steel will rust into iron oxide and the wood will rot into soil. But the PVC pipes, the window frames, and the credit cards will remain. In the stratigraphy of the future, millions of years from now, geologists will encounter a distinct white layer, or a series of anomalous synthetic veins running through the rock. These are the preserved skeletons of our subterranean infrastructure. These artifacts will serve as the most durable and unmistakable chemical autograph of a civilization that mastered the art of atomic fortification.
Chlorine is the only element that allows for the creation of a material so unyielding that it bypasses the biological cycle of decay, effectively freezing the shapes of our technology into the stone for eons. The geological cycle of chlorine also manifests in the creation of evaporite giants, massive mineral deposits that act as the Earth's long-term memory of vanished oceans. When a sea is cut off from the global supply and subjected to the relentless heat of the sun, the process of evaporation begins. This is a planetary scale distillation where the H2O is removed and the dissolved minerals are forced to reorganize into solid crystals. Chlorine, in the form of halite or rock salt, NaCl, is the primary result of this process. The salt flats of Bonneville in North America or the Salar de Uyuni in South America are the surface-level footprints of this phenomenon. However, the vast majority of these salt archives are buried miles beneath the surface, forming massive salt domes that can be thousands of feet thick. These structures are physically unique. Salt behaves like a slow-moving fluid over geological time, rising through denser rock layers like a bubble of oil in water. These salt diapirs act as impermeable seals, trapping pockets of natural gas and oil beneath them for hundreds of millions of years. In this capacity, chlorine functions as the geological vault keeper, ensuring that the energy of ancient forests and plankton remains preserved until tectonic forces or human drills reach them. Every grain of salt on a dinner table is a fragment of a lost world, a piece of a dried-up abyss that has remained chemically pure and structurally intact through the rise and fall of dinosaurs and the shifting of continents. The final and most extensive journey of chlorine occurs through the process of subduction and volcanic recycling. Over tens of millions of years, the chlorine-rich sediments of the ocean floor are pulled down into the Earth's mantle by the movement of tectonic plates. In this high-pressure, high-temperature environment, reaching over 2,000 degrees Fahrenheit, the salt is melted and reintegrated into the molten silicate soup of the planet's interior. This is the ultimate reset button for the element. The chlorine atoms will wait in the dark for hundreds of millions of years, circulating in the slow, heat-driven currents of the mantle until they are expelled back to the surface through volcanic eruptions in the form of hydrogen chloride gas. This atmospheric return closes a cycle that operates on a timescale so vast that the entire history of human civilization appears as a mere second in the life of the 17th element. As we look toward the deepest reaches of the future, the fate of chlorine on Earth is dictated by the thermal evolution of the solar system. In approximately 5 billion years, when the Sun expands into a red giant and the Earth's surface temperature rises toward 1,500 degrees Fahrenheit, the oceans will eventually evaporate. At this threshold, the despot will be liberated from its 3 billion-year liquid prison. The chlorides in the rock and the salts of the dried-up basins will be subjected to intense solar radiation and heat, eventually vaporizing the chlorine into a brilliant, glowing gas. As the Earth is consumed by the solar atmosphere, these chlorine atoms will be returned to the stellar environment from which they were born during the oxygen-burning phase of a massive star eons ago. The story of chlorine is thus a narrative of profound and uncompromising stability. It is the element of enforced peace, the substance that used its aggressive hunger for electrons to build the most stable and soluble bonds on the planet. We have used this green ghost to sanitize our cities, build our infrastructure, and target our medicines, relying on its predictable and ruthless chemistry to maintain the order of our civilization. Yet, the chlorine is entirely indifferent to these human applications. It does not care for the sterile water or the durable pipe. It simply follows the laws of thermodynamics and atomic geometry. It is the material of the limit case, providing a constant chemical baseline in a world of variables. To look at a salt crystal today is to touch the ultimate survivor of the cosmos. It is a material that was forged in fire, trapped by gravity, and concentrated by the sea. It has witnessed the arrival of life and will remain to see its end. Chlorine is our most Chesney biographer because its signature is written in our blood and our tears, in the white cliffs of our coastlines, and in the white veins of our future fossils. It is the silent architect of the biological and geological present, a substance that proves that even the most volatile and dangerous elements can be harnessed to become the permanent guardians of order and health. Every breath we take and every drop of water we consume is enabled by the green despot patrolling the boundaries of our world, reminding us that the stability of the universe is built upon the captured remnants of a celestial chaos that occurred long before the sun ever shone. Chlorine is the eternal sentry, a shimmering thread of salt and gas that connects the beginning of the stars to the ultimate future of an empty planet.